Hello, welcome to today's class. I want us to look at latent heat of vaporization. Now, we first take a look at the definition of these terms. Vaporization. Now, vaporization in a nutshell is just a process whereby a substance changes from its liquid state to its vapor state. Now, we also know that, yes, that for a substance to change from its liquid state to its vapor state, it occurs at a certain temperature, much like when we discussed latent heat. For lesson on latent heat, please check the description down below. Now, we say that yes, it occurs at a particular temperature. Now, that temperature at which a substance changes from its liquid state to its vapor state is known as boiling point, because it's only at boiling point that a substance changes from its liquid state to its vapor state, or water. Once water reaches its boiling point, as you apply heat to that water, nothing happens. Rather, it moves from its liquid state to its vapor state. Now, latent heat of vaporization. Now, latent heat of vaporization is nothing but the quantity of heat required to change unit mass of substance at its liquid state, or from its liquid state at boiling point to vapor without a change in temperature. Now, because there is no change in temperature, we now have that latent heat of vaporization, which is that quantity of heat. Quantity of heat is equal to mass of substance multiplied by the latent heat of vaporization. So we now have where Q is the quantity of heat, Of course, that quantity of heat is measured in joules. M is mass of substance. Mass of substance. It is measured in kilogram. Now, vaporization, which is L. L here is the specific latent heat of vaporization. So L is a specific latent heat of vaporization. Now, we now have also that, yes, assuming steam gives off heat, maybe if that steam gives off heat, if it releases a certain amount of energy, it can now come back to water. Or water, for this one, water can change from its liquid state into its vapor. Now, the case here is if there is a change in state here, there is a change in state, we now have the quantity of heat is equal to ml plus delta ml plus mc delta theta. Now, at this point, there is a change in state here with respect to temperature change. So we now have that, yes, we have explained 1, 2, 3. We now have this one is still mass. So we now have C is a specific heat capacity. Specific heat capacity measured in joule per kg per Kelvin. Then we now have delta theta to mean change in temperature. It can be in degrees Celsius, it can be in Kelvin. Whichever be the case, if it is given in Celsius, degrees Celsius, do not convert, use it that way. So temperature is measured either in degrees Celsius or in Kelvin. Now, having taken note of these two equations, let us now take some questions that will help us better understand this problem. A quantity of heat at 100 degrees Celsius condenses to water at the same temperature, releasing 6.9 times 10 raised to the power 4 joules of heat. Calculate the mass of condensed steam. Now here we are given that the specific latent heat of vaporization of water is 2.3 times 10 raised to the power 6 joules per kg per Kelvin. Now, solution. Given what we have at the board, now the quantity of steam at this is the temperature. Now, the temperature is 100 degrees Celsius, condenses to water at the same temperature. That means there is no change in temperature. Note it so. That you have 100 here does not mean that you will use it. There is no change in temperature here because it moves from water to steam at the same temperature. Releasing now the quantity of energy released, Q, the quantity of energy released is 6.9 times 10 raised to the power 4 joules. Calculate the mass of condensed steam. Now M is what we are looking for. Already we have here to be our L. L is 2.3 times 10 raised to the power 6. Now we employ our first formula. The only formula that will help us solve this problem is the one that says Q is ml. Now if we have Q is equal to ml, make m the subject because m is what you're looking for. If we make m the subject, we now have, of course, divide both sides by the coefficient of L, which is m. M is equal to Q over L. Once we have this, we substitute straight. If we substitute, we now have Q. Q is 6.9 times 10 raised to the power 4 all over L. L is 2.3 times 10 raised to the power 6. How do we do this? Because if you just press your calculator, you may get a wrong answer. How do we do it? This one is index number. We apply a lot of indices. Send this one up. If we send it up, we now have that M is equal to 6.9 times 10 raised to the power 4. And of course, if we send this one up, it becomes minus all over 2.3. Therefore, M will give us, at this point, you can now employ your calculator at this point, which will now give us 6.9 all over 2.3 times 10 raised to the power 4 minus 6 will give us what? Minus 2. So we now take this. If we now take this, we have that M is, from our calculator, we can now have that 6.9 divided by 2.3. Your answer, it will now give us 3. Therefore, mass will give us 3 times 10 raised to the power minus 2. Or, this value is something as writing 0.03 kg. So, this is the mass of steam that is condensed. That is. Now we'll take the next question. We'll take the second question. And this question says, so 10 raised to the power 6 joules of heat is required to boil off completely 2 kg of a certain liquid. Neglecting heat loss to the surroundings, what is the latent heat of vaporization of the liquids? Now, there is a question mark here. This question came out in JAMB 2015. JAMB 2015 question. Now, here we have from this. This is the quantity of heat here. So we now have that here, Q solution. Q, we'll read it together because they said 10 raised to power 6 joules of heat. That means the quantity of heat here is 10 raised to power 6 joules. It's required to boil off completely. The quantity of a certain liquid that was boiled off completely as steam is 2 kg. So we now have M is 2 kg. And the question now says neglect heat losses to the surrounding. Now, what is the latent heat of vaporization? Now, the latent heat of vaporization, L, is what you're looking for. Now, the only formula that will rhyme these is the one that says Q is ml. If I have Q is equal to ml, we're looking for L. Make L the subject. Because we're making L the subject, we divide by the coefficient of L. Coefficient of L is m. So if we divide both sides by m will go, and then we now have L left. We now have that L is Q over m. Now we substitute, put in these values. So if we substitute, we now have 10 raised to power 6 all over 2. Okay. Now, at this point, we can now apply our calculator. And of course, this one is simple. I need you to finish up the answer. Now, if we divide this by this, what do we have? And of course, you may be thinking that we have 2 divide this, which will give us what? 5. And then we now have 5 raised to power 6. And of course, it is not. If you pick this, it is not. And of course, 10 raised to power 6 is 1 million. So which we know that 10 raised to power 6 is 1 million. And 1 million is 1, 2, 3, 4, 5, 6. This is 1 million. 1 million over 2. Whatever that your answer is, please put it in the comment section. Help me share this piece of video. Tell your friends who may be writing JAMB this year. Please tell them to follow me on my Facebook page, and as well follow me on my YouTube for the full lesson. For the full lesson, please check the comment section. I will put the link to this full lesson in the comment section. Okay, well, let's go back to this before we summarize. Whatever answer you get is among these options here. So pick your correct answer and then let me know your correct answer in the comment section. Calculate the quantity of energy required to vaporize 50 grams of water initially at 80 degrees Celsius. If the specific heat capacity of water is 4.2 joules per gram per Kelvin. And here we are given that, yes, the specific latent heat of vaporization of water is 2,260 joules per grams. There are 2 things I want you to notice from here. This one, the mass is given in grams. Also, the specific heat capacity of water is also in grams. This one in gram. There is no need trying to convert. So you work with the value given to you. Now, we now have that, yes, they say calculate the quantity of heat or the quantity of energy. We can represent it as what? Question mark. Mass of water, M, is 50 grams. Initially at 80. Now, initial temperature, which is theta 1 is 80 degrees Celsius. Now, they said if the specific heat capacity of water, C, is 4.2 joules per grams per Kelvin, and then L is given to be 2260 joules per gram. Now, what is theta 2? And of course, we know that yes, for vaporization to take place, that is, for change of state from liquid, this is still water. The water is still at 80 degrees Celsius. For it to vaporize, it must hit 100 degrees Celsius. That water must get to 100 degrees Celsius. Therefore, theta 2 there is 100 degrees Celsius. Now, we move. Now, how do we calculate this? Now, we say that, yes, the quantity of energy released, or we say that energy given out is given by, or energy given out, which is Q. Q is given by ML plus, and of course, there is change of states occurred here. We change in temperature, which will now give us MC delta theta. So this is the energy we are looking for. Now we substitute here M, which is mass of water. Mass of water at this point is still water. Here, that same water will move to this, move to vapor. So we now have 50 multiplied by specific latent heat. Specific latent heat, we now have L. If we put value of L is 2260 plus mass of water 50 times specific heat capacity of water. Now, specific heat capacity, of course, is given to be 4.2 times temperature difference. Temperature difference here is 100 minus 80. And of course, this temperature difference here will give us what? 20. At this point, we can now bring in our calculator. So if we press our calculator, we now have 50 times 2,260, and it will give us 113,000 plus. Now we have here 50 times 4.2 times the difference here. The difference here is 20. So we now have 50 times 4.2 times 20, and it will give us 4,200. Now this 4,200 added to this, it will now give us that the quantity of energy required now to vaporize this will give us 117,200 joules. So this is the quantity of energy required to vaporize 50 grams of water that was initially at 80 degrees Celsius. Now we take the next question as well. Now take a look at this question. This question says, what is the difference in the amount of heat given out by 4 kg of steam and 4 kg of water when both cools from 100 degrees Celsius to 80 degrees Celsius? And here we are given that specific latent heat of steam, and of course solution. So all these whole grammar here, the specific latent heat of steam is 226000. While C, which is specific heat capacity, is given out 4,200 joules per kg per Kelvin. Now, they said what is the difference in the amount of heat given up? That means there are two different bodies here. There are two different quantities. We have the steam and we have that of water. All of them, two of them they are of equal mass. Okay, so we now have the temperature, final temperature is this, while this is the initial temperature. Now, I will tell you two different ways of solving this problem. Now, the simplest of them is that, and of course, we have that, yes, since there are two of them here, we say heat given out by water. Heat given out by water is equal to heat given out by steam. This is the simplest way of solving this. Now, heat given out by steam, by water, is, and of course, you know, MC delta theta for water. And of course, for steam, we have the specific latent heat there. We will now give us ML plus MC delta theta. So we can have here as water, we can have water here, we can have here as steam, we can have here as steam. Simple. So here will still be steam here. Okay. Now we have here will now be water, or we can still, since they are the same thing. So we can now have heat given out by water, mass of water times specific heat capacity of water. Mass of water, and of course M is 4 all through, both mass of water and mass of this. We now have theta 2 is 80, while theta 1 is 100 degrees Celsius. Okay, now in order to solve this, we have mass of water. We substitute mass of water. Mass of water is 4. 4 times specific heat capacity of water, 4,200 times temperature change. And of course, because this is cooling, we cannot say 80 minus 100. We'll still maintain this 100 minus 80, which will now give us 100 minus 80 here, which is equal to mass of steam 4 times specific latent heat of vaporization of steam, which is 226,000 plus, I'll write this one down here, mass of steam 4 times specific heat capacity of water now 4,200 times temperature change, which is I will take the temperature change here, I will take it at the same time 20, which is 100 minus 80. Okay, I will now have, at this point, we can now punch our calculator at this point. So which will now give us 4 times 4,200 times temperature change here is 20, which will now give us, I'll multiply this one first, which will now give me 4 times 2260, which will now give me 904,1234 plus 4 times 4,200 times the temperature change, which is 20. So this one gave me this. This one too will now give me 336,000. Remember, this side, I'll now calculate this side. If we calculate this side, we'll now have 4 times 4,200 times 20. And of course, the same thing we have here, it will give us the same thing, 336,000, which is equal to, I cannot add this. So if I add that one, 904,1234 plus 336,000 will now give me 937,600. This one is in joules. This one is in joules. So this is a heat given out by water, heat given out by steam. We cannot take the difference now because the question says, what is the difference in the amount of heat? So the difference will now be this minus this. Heat given out by steam, this value minus this value. At the end of the day, therefore, difference in energy or difference in heat will now give us 937,600 minus 336,000. Now the difference in the heat given out will now give us this minus this will give us 904,000 joules. So this is a difference in the mass, in the energy given out by the steam and that of water. Remember I told you that there are two different ways of solving it. Now instead of going through this, at this point, since heat given out by water is this and heat given out by steam is this, this one can still cancel out this one. You just calculate this time this. And of course this time this will now give us this value here. So this is the simplest way of solving this. Alright, this is where we'll draw the lesson to an end. Please, if you find this lesson interesting, kindly give it a thumbs up. Tell me how you feel about this lesson in the comment section. I want to know how you feel about this lesson. If it was interesting, tell me that that this lesson is interesting to you in the comment section. Please do well to share this video with your friends, and then we'll meet in our next lesson. Thank you very much.